Hello and welcome to today's lesson looking at the conservation of momentum. So in today's lesson we're going to try and understand and apply the conservation of momentum to different situations. So in today's lesson we're going to look at how we can put this conservation momentum law into a variety of events such as explosions and collisions. So we're going to look and try and calculate the momentum of one object, understand how the momentum can be conserved in a system, and then manipulate the conservation of momentum to calculate different values, which links into the following part of the specification, 6.5.5.2, the conservation of momentum. Now this is suitable for students carrying out AQA Combined Science with the physics section, and we'll look at the forces topic within that. So in collisions and explosions, the total momentum is always conserved. What that means is that the total momentum of a system before is the same as the total momentum of a system afterwards. So we can say that the momentum of object 1 plus the momentum of object 2 before must equal the same afterwards. So this means that individual objects can change their momentum in an event, but the overall momentum of the system, all of the objects, must stay constant. So for example, before a collision, object 1 may have a momentum of 2 kilogram meters per second, whilst object 2 could have a momentum of 0 kilogram meters per second. So it gives us a total momentum of the system of 2 kilogram meters per second. Then after a collision, both objects have 1 kilogram meters per second momentum, so the total momentum of the system is 2 kilogram meters per second. So what that tells us is that whilst the individual objects have changed momentum, the overall total momentum has stayed the same. So we can actually then expand on this equation, because previously we've looked at the equation for momentum, which is mass times velocity. So we can say the mass times velocity of object 1 before plus the mass times velocity of object 2 before must equal the mass times velocity of object 1 plus the mass times velocity of object 2 after the collision. Now in examination questions you'll be given all of the values in the system, the masses and the velocity except for one, and then asked to work out that missing value. So that will involve the rearrangement of this particular equation. So one of the most fundamental laws of physics is the conservation of momentum. It's actually based on Newton's third law of motion. In any collision or explosion, if there's no external force applied to the system, the total momentum of the entire system is the same before as it is after the collision. So we can pop that into a mathematical equation and say that the total momentum before equals the total momentum after, or the mass before times the velocity before equals the mass after times the velocity after, which can be shown with the following animation of a Newton's cradle. So in the collision, momentum is conserved so that the balls must have a consistent product of mass times by velocity, and because the mass of each ball is the same, the velocity of each ball will be the same. The balls will move at the same distance up the cradle as each other. Another example could be these two colliding cherries. So in the collision, momentum is conserved. So as the cherries stop moving, the water then moves to conserve the momentum before and after the collision. So when we're looking at collisions, we've got to consider the total momentum of a system. So for a system of objects, the total momentum of a system before equals the total momentum of a system after, as long as there's no external forces on the system. Now another way of saying this is saying that basically the system is a closed system. So if we look at this particular example on the screen, so we've got two objects, object A, object B. They collide together to then stick together to form object AB. So we know that the momentum before equals the momentum after. So the momentum of A plus the momentum of B before equals the momentum of AB afterwards. Now we consider any system which has at least one dynamic, one moving object before contact at collision. So let's look at an example question. So in this particular situation, you've got an object A, which has a mass of 2 kilograms and a velocity of 5 meters per second, and object B, which has a mass of 4 kilograms and a velocity of 0 meters per second, it's not moving, and then they collide together, they stick together, and they move off. So what would the velocity be of the two balls stuck together after the collision? Well, what you do is you carry out step 1 first. You work out the momentum of the side of the collision you can do, And the side you can do is the momentum before the collision, because you've got all the information. So you work out the momentum of object A, 2 times by 5, because it's mass times by velocity. You work out the momentum of object B, it's 4 times by 0, mass times by velocity, so it's 10 plus 0, so the momentum before is 10 kilogram meters per second. Then remember is step 2, momentum before a collision equals the momentum after a collision for the total system. So before the total momentum was 10 kilogram meters per second, afterwards it'll be 10 kilogram meters per second. Then you use the equation momentum equals mass times by velocity, rearrange it to work out what you want to work out. So the question asks us to work out velocity. So we say velocity is momentum over mass. So you do 10 divided by the mass, which we know if the two balls are stuck together, it's 2 and 4 stuck together. So the total mass will be 6. So you do 10 divided by 6 and you get an answer of 1.7 meters per second. Now when you've calculated your answer, you then carry out a logic check. Does the answer look sensible? Now let's think about it. There's only one object moving before the collision and it's got a mass of 2 kilograms. So afterwards, the object moving has a mass of 6 kilograms. So the object in motion is gotten more massive, so therefore to compensate, it'll be moving slower. So the answer has to be less than 5, and it is, because 1.7 is less than 5. The answer passes our logic check. Now let's look at another event, an explosion. Now by definition, the total momentum of an explosion has to equal 0, because before an explosion, the object is not moving. So because we know momentum is mass times by velocity, this means the total momentum must be 0. But after the explosion occurs, the object will break into 2 fragments, simplified, and then we've got our 2 fragments produced. Now these objects are moving, so they'll have a non-zero momentum. But the overall momentum of the system has to be equal to 0. So how does that work? To conserve momentum. Well, this works as the individual momentums of the fragments must have opposite signs. One has a positive sign, one has a negative sign. This occurs because the 2 fragments are moving in opposite directions, and we denote opposite directions in physics by having one have a negative sign. So therefore, what will happen is when we add these 2 values together, they will add up to equal 0, so we'll conserve our momentum. So the 2 values will sum. So for example, plus 20 kilogram meters per second plus minus 20 kilogram meters per second equals 0 kilogram meters per second. So let's just look at this again. In an explosion, when 2 objects A and B explode, when they start at rest, the momentum is conserved. So momentum before will equal 0 because the object is at rest. Momentum afterwards will be momentum of A plus momentum of B. So because we know momentum before equals momentum after, we know that 0 equals momentum of A plus momentum of B. So we can take one of them to the other side to become negative. So momentum of A will equal minus momentum of B, which makes sense because they are moving opposite directions after the explosion. But remember, this is only true when both objects start at rest and move apart from each other. So let's look at the following example. So we've got a bomb before an explosion with a mass of 10 kilogram meters per second and a 0 velocity. It's not moving. Then after the explosion, it breaks into 2 fragments, one of mass 3 kilograms and we don't know its velocity, the other of a mass 7 kilograms and we know it's got a velocity of 2 meters per second. So what's the velocity of bomb fragment 1? Well, step 1, work out the momentum for the fragment which you can, and you know the mass of fragment 2, you know the velocity of fragment 2. So momentum is mass times by velocity, so it's 7 times by 2, our answer is 14 kilogram meters per second. Step 2, you know that the total momentum of the system before is 0, so the total momentum of the system afterwards is 0, so if fragment 2 has plus 14 kilogram meters per second, fragment 1 must have a momentum minus 14 kilogram meters per second, because when they add up it equals 0. What we then do is we use the equation momentum equals mass times by velocity to work out your velocity, or the value you would want, which is velocity in this particular example. So velocity is momentum over mass, it's minus 14 over 3, and it's minus 4.7 meters per second. Should the negative sign be there? Yes, it should, because fragment 1 is moving in the opposite direction to fragment 2. Fragment 2 has a positive momentum, so fragment 1 has a negative momentum. We then do our logic check, and we look at fragment 2. It's got a higher mass than fragment 1, so therefore it should have a lower velocity than fragment 1. And does it? Well, yes, our calculated answer is minus 4.7, so it has a smaller mass, therefore a higher velocity. So it all makes sense. It passes our logic check. So let's now have a look at this in an example of something called recoil. So for example, firing a gun can lead to what we call a recoil in these particular examples. So many objects, when involved in an explosion, you get a recoil of the object. But why do you do that? Well, let's consider the gun and the bullet. So before the gun is fired, before the explosion occurs, the gun isn't moving, the bullet isn't moving. So the system has no momentum. So the total momentum of the gun and the bullet is 0 kilogram meters per second. So the total momentum before is equal to 0. Now, therefore, after it's been fired, the bullet will be fired out of the gun, so we'll have a momentum. But then to conserve momentum, to ensure the total momentum of the system is 0, the gun must also have a negative momentum of the same magnitude as the bullet. So when they add together, it equals 0 to get your total momentum after to equal 0. So let's have a think what's happening. When the object is fired, the gun has a momentum, the bullet has a momentum, so they cancel out to give the value of 0. This means the gun goes in the opposite direction to the bullet, the gun has recoiled. So let's think about what's going to take place though, because momentum has to be the same for the bullet and the gun. That because the bullet has a lower mass, it will have a higher velocity. Because the gun has a higher mass than the bullet, it will have a lower velocity than the bullet. So the gun must have a lower velocity than the bullet to have the same magnitude of momentum. So they'll have the same values of momentum to cancel out and give 0. So the momentum of the bullet equals the momentum of the gun. So the mass of the bullet times the velocity of the bullet equals the mass of the gun times the velocity of the gun, which we can then rearrange to say 0 equals the momentum of the gun minus the momentum of the bullet, or mg times vg minus mb times vb. And remember, both of these values have to be the same because it has to equal out to 0. So you could be given 3 of those terms and asked to work out the 4th in an examination style question. So 1 is a plus and 1 is a minus as they move in different directions. And in a collision or explosion, you tend to find the larger the mass of the object, the lower the velocity to conserve the momentum. And we actually observe this effect in all guns. So what have we learned in this particular lesson? In a closed system, the total momentum before an event is equal to the total momentum after the event. We call that idea the conservation of momentum. You should be able to use this concept of momentum as a model to describe and explain examples of momentums in events like collisions or explosions. So if we're being successful, and we've learned in today's lesson, we can calculate the momentum for an object, understand how the momentum can be conserved for a system, and manipulate the conservation of momentum to calculate different values. I hope you've had a lovely day, and I hope you've enjoyed this lesson looking at momentum and the conservation of momentum. Take care and have a lovely day.